Hi everyone. Let's go ahead and get started with attention is all you need. This is research paper proposed by Google in 2017 and this was the research paper which had changed the field of natural language processing. So basically at this time Google has proposed a transformer and the transformer uses inside that attention. So they said that this is attention and you don't need now any sequential to sequential traditional RNN and LSTM networks. Earlier, there were, the LSTM and RNN based networks used to be something like this. In that, you can understand that how it used to work at that time. At that time, what used to happen there was encoder and then decoder. All right. So in these encoder and the decoder part, you will be seeing that in these two encoder and decoder part, there were, it used to contain their RNN and LSTM networks here. So the part of encoder you see there, this used to encode the input data and decoder used to decode the data given from the encoder and also taking from the decoder as well. So in this case, let's say hypothetically you are given this input, how are you? And then these goes inside this encoder 1, 2, 3 and 4 cell. Let's say in these 4 cell it goes there, and thereafter processing of these one by one, and then final state, this is final hidden state used to come outside. Once this final hidden state comes outside, thereafter it takes this one as the input to the decoder, and thereafter then there was a start token which produces the first output, and thereafter the first output comes as the input to the second cell of the decoder, and as well along with that the output of the hidden state from the decoder state 1. So basically you see from here. So this process was quite complex, and for long-term dependency there was the problem. So basically what I mean to say here, let's say you have very long sentence and you want to get the context of this particular word in your sentence, and then for this particular word, let's say let me just zoom out this then. Yeah, so let's say you want output for this one. So the problem was this, that it has to get the hidden state for all these words. Let's say there are hundreds of words or thousands of the words. In that case, the dependency was on all these previous words, and in that case only one single hidden layer was getting produced as the output. So that was the huge problem in the traditional RNN and LSTM sequential to sequential methods. So Google came up with new solution, and they proposed here attention network. So the way attention works, in that way it automatically, actually let me just show you here that, so the way attention works, it automatically let me just show you here inside, in fact here. So it automatically find out the relation between the words. Basically it says that how important a particular word for inference. For example, if you see in our current set of the example where we are seeing here, let's say you have here the law will never be perfect. All right, so this is something like that you are trying to understand that. So this is example of the self-attention. So in self-attention, what happens here, that it says that you are given here a long sentence, this whole sentence here, and then it says that how these words are correlated with other words in the same sentence. So it says that this the is highly correlated, or it is quite correlated with this law there. Thereafter it also say that this law is also correlated with this the, and then also it is correlated with the law itself, and there are also, if you see there here, this line, a very fine line is also coming here at this dot. All right, very fine line is coming here at the dot. That's mean this is also connected with some, a very small attention here at the end of the sentence as well. So these were the problem with the traditional sequential to sequential network, which was solved with this attention network. All right, so let's try to understand that. Let's try to understand that how this whole architecture actually works here. Okay, so in this paper, we are going to review this paper. So in this paper, first of all, they start with their, the abstract. In abstract, they say that they had achieved 28.4 blue on WMT 2014 English to German translation task. So basically this English to German translation task dataset was used for the evaluation and the development of this model. Okay. Thereafter, in introduction, they actually describe that the traditional problem with the recurrent neural network, long-term, short-term memory, LSTM, and the gated neural network like the GRU networks there. So these are the problem like I described you earlier. So they say that at any particular state HT, it is the function of all the previous hidden state HT minus 1 and the position T there. So basically what they are saying there that at any state, let's say you have a very large sentence, and in this very large sentence you are trying to identify the state at this particular position. All right, so this is a state where I say that it is HT, and there are so many states here. Before that, there we have here HT minus 1, and then this HT minus 1 is the function of this one. This HT is the function of HT minus 1. So basically this is a function of this one. You can say that it is the function of HT minus 1 and XT. So this is kind of the recurrent. Now you know that HT minus 1 is the function of HT minus 2. So basically this one you can say that this is function of, let me just scroll it down till just you can see that here. So this one is function of HT minus 1 and XT here, and then this HT minus 1 is a function of HT minus 2 and XT minus 1. So it is something like it just goes on. All right. So that's the problem with the traditional LSTM and RNN encoder and decoder. So that problem they solved here using this attention methods here. So in this, let's discuss this model architecture directly. So here they describe that they have input sequence which is represented as x1, x2, x3, xn, and if this encoder, so basically they are saying that suppose that there is encoder, so basically they are saying that here is input x and then there is encoder, and then this encoder is producing here output z here. All right, so you see there this is another representation output z, and then this z goes to the decoder part here, and then this decoder produces here output as y. So these x you can say that it is function of like x1, x2, xn, and similarly this z will be also produced as the z1, z2, and zn. But thereafter at the output you will see there it is y1, y2, and this is ym. So this m and n are not the same. So what happens here, this z, you can say that this is kind of context embeddings here. All right, so this one is the context embedding, and you will see here these are not same. As you see here, n and n input and output will be same there, but the target the number of tokens into the target output won't be same. For example, let's say if your encoder decoder is working for any translation task, then probably in your input you have 10 words, but in output you might have 9 words, 8 words, or more than 10 words, or more than 10 tokens. So that means that the number of the tokens at the output will not match the number of tokens in the input. All right, so let's see how this overall this transformer works here. So the heart of this transformer is inside this only. All right, so in this heart, how this works here, their input comes and then embedding happens to this input, and thereafter the positional encoding is also being done here, and then these goes to here the multi-head attention neural networks, and then feed forward network goes, and then finally this comes here. All right, so this seems like a little bit confusing maybe to you. So what we can do here, we can first of all understand that how this overall attention network actually works. Thereafter, once it is clear to you that how this attention works, then it will be clear to you that how other architecture works. All right, so you just scroll it down a little, this attention paper, you will see here scaled dot product attention network and multi-head attention. So these are the two network here. So basically what happens here, they define that there are three vector Q, K and V. So these are the three vector, and these three vectors they are taking together, and then finally they are getting this final context out of these. So what are the important the parameters in this attention dot attention network? So basically you have here the multiplication, and then there is a scaling, and there is masking happens, and then there is a softmax, and then finally a multiplication happens. Okay, so this could be a little more to you, so I'm just gonna delete those, and then I'm going to tell you that how you get first Q, K and V, and thereafter I'll explain you that how this multiplication happens here. So let's say you have your input here as traditional input. Once you have your input, just let me scroll it here. So once you have your input, then a linear layer is applied here. So this particular input produces here output, and then this output is Q, K and V. So basically you can say that there are three linear layer in here. So in these three linear layer, you can say that one is Q, another one is K, another one is V is the output, something like that you can say it here. Okay, so that was overlapping, so I just removed that. So basically you can also show it in more compact way, that you have your input, and then these input goes from these three layers. In these three layer you see that one linear layer, another linear layer, and here is another linear layer, and the weight of these linear layer you can represent as here WQ and WK, and here is WV. So finally at output you get here the Q vector, so that Q vector is WQ into X, and then you also get here the K vector, that is WK into X, and then you get here the V vector, that is the WV into X. So basically you can say Q, K and V, which is the query, key and value, these are linear projection of your input into a vector space. So you can assume that there is a vector space here. Okay, so there is a vector space, and in this vector space all these queries, let's say these are the queries mapped here, and then also here the values are also projected here, and you can also assume that in the same vector space like we are seeing here, so values are also projected here. All right. Okay, so that's how this is going to work. And then you get here this q, k, and v vector, and then these vector goes as the multiplication of q and k. So how this q and k works again in the vector space, let me just explain this to you. Let's say you have a word here, and that word you want to, let's say you have a word here, this you have, let's say, a query which is word, and then for this particular query you want to understand that how much attention it is going to get from the different words, that you can understand that, like let's say you have this query and all these are v1, v2 and v3, and here k1, k2, and here you have k3. All right. So this query Q is going to first match with all these keys K1, K2, K3, and thereafter it's going to multiply. Basically a dot product is going to happen here. So let's say this query you say that as Qn. So Q1 into K1 happens, and then Q1 and K2 happens, and then Q1 and K3 happens. So you see there a dot product, higher value means higher probability. All right. So these happens. Thereafter a softmax is taken for these. All right. So you can say that it is a function of softmax here. All right. And thereafter a multiplication of v vector happens here, which is like v1, v2 and v3, like that. So you can say that attention, if you say by seeing the above formula, so you can say that attention is a function of q, k and v here. And how do you calculate that? So the formula is here. You apply here softmax, and inside that you put here q into k of transpose divided by d underscore dk, and then multiplied by v. So now the question is, what is this dk? So the dk is like how they have explained here, that dk is something they divide by under root dk, so that they can actually they can regularize the model. Otherwise, if they multiply q and kt together, the value of this multiplication becomes so large, so the gradient calculation becomes difficult. But if they divide it by underscore dk, where dk is the model dimension or embedding dimension, so the value of q and k transpose becomes low, and then there is a gradient, and then finally they also multiplied by here v here. So how do you understand this? Again, you can say that q is the query for which a question is being searched. For example, you search on YouTube videos, so you search something like, let's say, attention. You search there attention. So this attention becomes here a query in YouTube videos, and then videos title which you see there, those becomes their keys. So the more they score with these matching keys, more those will get boosted, and then finally the video itself becomes their value. Video itself is value here. So like that you can understand that these query, key and value combination together. Now you see here is the formula which I was explaining you. Alright, attention q k v equal to the softmax k q into k transpose and divided by under root dk and v. Okay, so let's see how then this multi-head attention network works here. So in terms of the multi-head attention, how this works here, they take this single attention networks and thereafter they combine it multiple times in parallel, and thereafter they concatenate these results together, and thereafter finally they also pass this with the different with the another linear layer for the output. So that is what that is what shown here. All right, so what happens there, input comes there, so once this input comes from here, then it is divided as Q, K and V. And one more thing you see here, there is also a skip connection. So this multi-head is nothing more than there is attention networks, but these attention networks are in parallel attention networks. So each of these are attention networks, and then finally it produces the output. So once it goes there, produces the output, all these concatenation happens here. All right, so these concatenation happens, so it becomes a single a single networks, and thereafter again a linear layer is applied here. So after the linear layer you will get the output here, and then this output and then the previous output where is the residual network, these gets combined together, then the adding and then this normalization layer is applied there. Thereafter another feed forward neural networks and addition and normalization happens there. So this is a single block of the encoder, this whole thing. So there are n such number of the encoders there, and in transformer network they have taken a 6 encoder layer, similar encoder layers, and similarly there are 6 decoder layer, a similar decoder layer, you can say that. So what happens in the transformer, everything you see, what you see here is exactly same what you see here, other than this particular thing. So in this what happens, they have applied here additional masked multi-head network just before the multi-head attention network. So in this case what happens, whatever the output is generated here, this output is again coming back here. All right, and then in this output they are passing with this multi-head attention network so that they can focus on the they can actually understand the current context of the generated output. Okay, so this output which comes from there, this one you can say that this is a query. And what are these two input which you see here, those you can understand that with these individual multi-headed attentions, that there is value and key. So the first one is the value, another one is the key here. All right, and then this one which is coming from there, that one, this particular thing is actually a query. So the query comes from the output, and then keys and values are coming from the encoder, then they get combined together with multi-head attention network, and then they goes out of that. There is another important function of this masked multi-head attention network, that let's say you have this large sequence output and you are currently here. All right, and you are currently here, and these are W1, W2, W3, W4 and W5. So W5 is expected output, but your model has not reached till W5. So your model need to take the output context for only W1, W2 and W3 and W4 together. It should not take W5. So in that case what happens there is masked attention network. So in the masked attention network, they multiply these 1, 1, 1, and this becomes 0. So this goes, this goes out of context. So this is also known as causal learning. So that it should not take the context for the future tokens. Instead, it should be taking the context only for these previous tokens. All right, so that is how it finally generates the output. Let's go ahead and try to see that here with another architecture which is explained here. So in this architecture, the same thing is explained again, but in a little bit more better way. So you have input sequence here in some language. Then this input sequence gets converted as the embedding vector. Along with that, there is a position encoding. So what is this position encoding? So in these position you see there, these tokens which you see, the position also matters there. So there need to be some encoding method so that the position can be known there. So they have come up with the two formula that there for the position encoding. So one sinusoidal based formula where you can simply apply. Just let me scroll it a little bit down. You will see those formula. Yeah. So here it is. So for position encoding, they have sinusoidal and the cosine, the network there so that they can, encode those values. So let's say, let's come back here again. And in this position encoding, you will be seeing these values, these encoding which you are having, these are function of 2-3 things you have seen there. One is the position and one is the index itself, and then the dimension of the model here. Okay, so what is this I index? I is like, let's say a vector is generated, so what is a particular index is there, and then this position is the position number in the token, I mean in the sentence for that particular token. And for even position they use sine function, and for odd position they use here the cos function. So the sine and cos, you can understand that they are like this only. Alright, and the sine and cosine values varies in very small manner, and they are also kind of consistent. So if you add this position encoding with the traditional learned embedding together, it will not change the overall embedding, but it will improve the output. Yeah, so thereafter you will see here that then these multi-head and layer normalization part, etc. Then finally these encoded vector comes out here. So those are the context vector actually, and then these context vector goes again here inside the decoder part, and also this query comes from here. So this is the part of the auto regression as you see here. And for this auto regression again, output embedding is there. So then embedding gets generated for these, and then again these goes here, and then the masking is also applied there. So that is how this overall architecture works here. I hope that you have understood that this overall architecture of the attention network, that how it works. Let's go ahead and scroll it down a little and just understand that how better it is than the traditional recurrent neural network. Since this performs in parallel, so its performance is quite high here. For example, the traditional sequence to sequence network, we have seen that those perform sequentially, so they take a lot of time for sequence operation, which is ON there. That means they depends that total number of the input sequence, okay, and only then you will be getting the output in the traditional LSTM. But if you apply the transformers, in the transformer what happens here, they have all these in parallel here. Alright, so all these can be calculated parallelly. That's how they do this. So you see, you can calculate the attention, the parallelly. So that is why you see the sequential operation is here the constant. And other than that, the complexity layer, you will understand that this D is the dimension there, and N square is the number of tokens. So for each of these tokens, it calculates the attention for all other tokens. So basically it will calculate N square number of times there, and the size of the embeddings for each of these attentions there, which you will be seeing there, that is the D. So you multiply that with the D. So it becomes N square into D. So that's the complexity here. And if N is a lot lesser than the D, generally which happens, so N is the input context size. If N is smaller than D, then the complexity of self-attention neural networks are quite less than the traditional sequential to sequential networks. Alright, so this is all about in this lesson. Thanks a lot for watching this. I hope that you have understood that how this overall transformer architecture works. If you have any confusion or any doubt or the question, you can comment that. I'll try to solve that. And if you have liked this video, please do subscribe this channel. Thank you so much.